Okay, so yeah, I'm Martin. I am a research scientist in Google's flood forecasting team. And yeah, my goal for this talk is really to give you an introduction and an overview to the work that we've done around deep learning for flood forecasting, some of the research behind it, or probably a lot of the research behind it actually, as well as some of the operational flood forecasting that we're actually doing to really warn people about floods sort of anywhere on Earth. So brief overview of the presentation. I will start with a bit of motivation. I think there's also probably a lot of people on the call who are not really familiar with flood forecasting or hydrology in general. And so I'll start with a bit of motivation and explain sort of what actually are we trying to model here. I will then show some of the results, some of the benchmarks to see how well we can actually model these floods. I'll go a bit into the architecture of especially specifics that are interesting for an operational model, of how to build the model so that it can be used operationally. And then finally, I'll give a bit of a glimpse into the sort of current research and what's hopefully or maybe becoming sort of the next generation of deep learning for flood forecasting models. So let's start with motivation. And of course, the first question we need to ask ourselves is, why should we even predicting floods in the first place? And that answer is, I think, probably relatively obvious, but I go through it anyways. So it turns out that floods are actually one of the deadliest natural disasters in the world. They account for about half of the people that are affected by weather-related disasters. So they're quite a bad thing, obviously. But at the same time, it turns out that if you have early warning systems and you can warn people ahead of time, this is an extremely effective way of avoiding these mortalities and avoiding these losses and damages. So there's this statistic where disaster mortality is 8 times higher in the places that are lacking these early warning systems. And so having early warning systems in place globally is really an extremely effective way of helping people. So I think I've probably convinced you that predicting floods is a worthwhile cause. The second question we often get asked is, of course, why would Google specifically care about predicting floods? And the reason for that is really that Google is the place where people come when they look for information. And that's generally true, but it's especially true in sort of times of crisis. And a flood hitting your neighborhood certainly qualifies as a crisis, I would say. And so Google being able to give you that information of whether it's being predicted that your neighborhood or the place that you're at right now is at danger of flooding is really quite a useful thing. So Google started this effort about 6 or 7 years ago, I think. And it's come quite a long way since then, where today we have this global model running. It's publicly, freely accessible. You can actually go to this website with the URL at the bottom here. And what you see on that website, we call it the Flood Hub, is really a global view of all of the places that we're issuing predictions for. So what you see on this map is these different colored pins, and the different colors sort of indicate the severity. So where it's green, that essentially means that we're predicting that nothing out of the ordinary is happening. And then the yellow and red and dark red colors mean that we're predicting an event of a higher severity. So the colors are based on return periods, meaning, for example, the red color is indicating an event that we would only expect to happen once in every 5 years in this location. So something relatively rare. And then the dark red is once in every 20 years. So even more rare. And then you can actually zoom in to each of these places. This is actually Australia. Maybe there's people around who know this area. Where you can click on each of these individual pins, which are sort of the points along the river, and you can see on the left our forecast. This is a screenshot I took a few days ago for the Manning River, and you can see how we're predicting the flow to actually rise quite significantly. And I looked a bit in the news, and I think there seems to be at least something happening there, so it's probably at least to some degree correct, which is nice. And you can sort of see this for all of the points on this map, and sort of explore yourself, maybe the region that perfect, currently evacuating. So yeah, you can sort of explore there yourself. And this Flood Hub is really sort of the UI that we have for more expert users who really want to explore the broader area, maybe even globally. It also has an API for programmatic access. But of course, we have other channels of more immediately warning people, and I'll get to that in a second. So what we have here is kind of the overall modeling chain that we follow in order to issue these flood forecasts. And there's really three parts to it. We start by the hydrologic model. This is the model that I'll actually focus on for the most part of this talk. The task of the hydrologic model is really to predict the amount of stream flow that's sort of flowing in a river at any point in time. And stream flow really is just the cubic meters per second that are flowing, so sort of the volume of water that's in the river at the moment, or at a certain point at least. And then we have this hydrologic model stream flow forecast, and we pass that to the inundation model. The inundation model has the task of turning that stream flow forecast into a spatial map of which places things are going to be flooded or inundated and which places are not going to be flooded. And then finally, of course, we have to make sure that those flood warnings actually get to the people. And so for that, we have, for one, the Flood Hub that I showed earlier, but also we send push notifications to Android phones in certain regions. We show warnings in Google Search and Google Maps. And actually for the river that I just showed in Australia, I believe Google Search is actually showing such a warning if you look for the area. And so this is really how we make sure to inform people who might be affected by this flood situation. I will note that we do not run an inundation model for all of the places that we run a hydrologic model, for the reason that we're not able to accurately model inundation everywhere, and we don't have the historical data that we need everywhere to build these inundation models. So in some places, you will only see a hydrologic model forecast, but that already tells you sort of if the stream flow levels are extremely high, then probably there will also, or then at least the likelihood is higher that there will also be some inundation. So before I go into the details of how exactly the hydrologic model works, let me introduce a little bit more of terminology, because that will be sort of relevant throughout the remainder of the talk. I already said that the goal of the hydrologic model is to predict stream flow. And stream flow, as I said, is just the cubic meters per second of water flowing past a point in a river. And this point in the river, here we have the Blue River, and we have this red point on along that river. And we can call that red point a gauge or a gauging station. And in the ideal case, this is actually a physical gauging station where there is some measurement device that has historically been measuring the stream flow levels at this point. And so we have historical records of the stream flow for this location. But of course, there is also a lot of places that we want to make predictions for that are ungauged, so that do not have a gauging location at that red point, at this outlet of this upstream area. And both are kind of interesting and relevant tasks to be able to do, making predictions in gauged and in ungauged places. And I'll get to that later in the talk. So I already said that the upstream area of this gauge is, of course, the sort of the relevant thing to know when I want to make a streamflow prediction. So I would like to know, especially the rainfall and the precipitation, but also other sort of weather variables of this upstream area. And this upstream area is what we call the basin or the catchment. It's essentially defined by the elevation profile of the area. And you can imagine it as if I put a drop of water anywhere inside of that orange boundary, it will follow the elevation profile, and it will eventually end up draining through that red point. If I put a drop of water anywhere outside of that orange boundary line, it will drain elsewhere, because the elevation profile is just going to lead it elsewhere. So the basin is defined by the elevation profile, and it sort of tells us the area that is going to be interesting, or that we need to look at when we want to make a streamflow prediction at this red gauge location. Okay, so this is the terminology. Streamflow, basin, and gauged. And now if we look at this modeling problem from a bit of a more conceptual point of view of the inputs and the targets that we have, it's going to look something like this, where on the left, we have our weather input data. We also call them meteorological forcing information. And so those are things like precipitation, maybe solar radiation and temperature. Could also be a number of additional variables. And typically what we do if we want to make a daily prediction, we pass the model a historical context of about 1 year of these weather data, so that it can track how much precipitation has happened in sort of the recent past. And we use a year so that it can also accumulate things like snow that has fallen over the winter season and that starts to melt during the spring season when the temperatures rise again. So we have these meteorological weather inputs, and then we have static attributes, which are things like the average soil type of that basin, maybe the elevation or the types of land cover. And so those are kind of variables that are relevant or that determine how the basin reacts to precipitation events. So how the precipitation transforms into stream flow, of course, that depends on how the elevation profile is, what kind of soil types there are, and so on. So we have all of these input data, we feed them into some sort of model, and I'll get to the model in the next slide. And we try to make that model predict the stream flow time series at any point in time. So the red hydrograph here, the red time series, is essentially our labels, our target data. Now, this modeling problem is nothing new. Hydrologists have been trying to solve this and have been building models to predict stream flow for many, many decades, if not longer. And traditionally, classically, what people have come up with, or one of the types of models that people have come up with, is something like this, sort of a conceptual hydrologic model. It doesn't matter too much all of the things that are going on here. What you need to sort of understand is that the way that people have tried to model these systems is by very explicitly trying to account for all of the processes that might happen in nature. So you see things here like there is this snow bucket, which tracks how much snow there is in the basin. So there's probably incoming precipitation during low temperatures. The filling level of that snow bucket would rise. And then if the temperatures increase, the snow bucket would sort of start draining again. And then you have a soil moisture bucket, which tracks how wet the soil is and how much water is sort of stored in the soil. And you have all of these relationships between these buckets. And the task of modeling stream flow with such a model now is to, first of all, figure out the sort of the connectivity and all of the processes that are represented here, and then figure out all of the parameters of how fast do each of these buckets drain into each other, and maybe what is the capacity of those buckets, and so on. So you can imagine that this is quite a tedious task. It's quite hard to make this model accurately predict stream flow, because it's just virtually impossible to measure all of these things for every point inside of that basin in reality. But this is how stream flow was traditionally modeled. There's also other types of models that people have built, but this is certainly one of the most popular type of model structure. And then about 5 or 6 years ago, people actually figured out that there's another way of going about this modeling exercise, where you don't very explicitly model all of the processes, but rather you take a much more data-driven stance, and you take a time series data-driven model. Specifically, people figured out that long short-term memory networks, or LSTMs, work extremely well for this task. And so what you do there is you have this time series deep learning model, and you just feed it all of the data that you would typically feed your conceptual model. And you perform backpropagation to make that model learn how to transform all of these inputs into your stream flow response. So the model is not explicitly, you do not prescribe all of the processes that you prescribe in the conceptual case, but rather you have the model sort of figure out by itself what are the relevant processes and what are the relevant states that it needs to track in order to make an accurate stream flow prediction. So this deep learning sort of paradigm is in some sense very different from the classical hydrologic model, in that you do not explicitly prescribe any of the processes. The name of the model is LSTM, or long short-term memory network. It's been invented in like the 80s, but it's only been introduced to hydrology much more recently. And it has become sort of the state of the art in hydrologic modeling, really. So these two models look very different, but actually on a very high level, there is some similarity at least. And that similarity is that both of these models are state space models. I think I've already sort of explained how the classical model has these states that it tracks over time. And essentially it has a function that takes the input and decides how to update all of these bucket levels. And then it has another function that decides, given the bucket levels, what is the current stream flow response. And the data-driven deep learning model, the LSTM, is somewhat similar in the sense that it is also tracking a state over time. So it also has a function that decides, given the current inputs, how do I update my current state? And then it has a function, given the current state, what is my output? What is my streamflow response? The difference is that for the LSTM, the state is just a vector of a certain size, and the model figures out by itself what to write into that state and what to read from that state. Whereas on the left, we have to prescribe the meaning of the states. But at a high level, there's the similarity, and that sort of makes sense because in nature, there are these states. Like in nature, there is the sort of the soil moisture and there is the snow. And so it makes sense to have a model that is able to track such states over time. But again, they're different in the sense that the deep learning model is much more flexible and learning these processes from scratch. So as I said, people figured out that LSTMs might be a good way of going about hydrologic modeling about 5 or 6 years ago. And of course, the first thing that people did was to see, so how do they compare? How do these new deep learning models compare against classical hydrologic models? And so we did a whole bunch of benchmarks, and also other groups did a whole bunch of benchmarks to try and figure out how they compare. And the way that we often go about benchmarking in hydrology is by means of these plots here. So you'll see a number of these plots throughout the remainder of the talk, and I'll take a minute to kind of describe what we're seeing here. So what we've done here is we have an experiment where we have historical streamflow records from about 500 gauge stations. Yeah, LSTM is the name. From about 500 gauge stations all across the continental United States. And we have historical streamflow records for them, so we can train and evaluate models on each of those basins. And then we have a number of different models. So each of the lines that you see here is the results for a different classical hydrologic model. And then the x-axis is the Nash-Sutcliffe efficiency, or NSE, which is, for people outside of hydrology, this might be a metric known as R square. Really, all you need to know is that larger values are better. The best value that you can achieve is 1. So you want your curves to be as far to the right as possible, essentially. And then on the y-axis, we have the cumulative distribution function across those 500 basins. So what that means is essentially we take the 500 metrics, the metrics from the 500 different gauging locations, we calculate this NSE value for each one of them, and we get this cumulative distribution functions. And so if they're further right, they will be so curves that are further to the right are better. So we have all of these metrics for all of the conceptual models, and of course that doesn't really tell you much. But now if I add the curve for the LSTM, you can see that there is this massive gap where the LSTM is really doing better than any of the classical hydrologic models. And that's not only true for this individual benchmark, it's generally been shown to be true for the benchmarks that people have done also outside of the US and in other places. So that's great. LSTMs work very well. We've had a massive boost now in our ability to model streamflow. But of course, the question is a bit, how is it possible that decades of hydrological research are sort of blown out of the water with this LSTM? And one of the reasons, or one of the key differences that we have here between these two types of models is a specific way of how they're trained. I didn't mention this before, but these classical hydrologic models, they perform best if you train an individual model for each place individually. So what you end up doing is, if you have these 500 basins, you end up with 500 sort of copies of your model that are each kind of hyper-focused to the individual place. And so the idea is that if I train a model for my individual place, it'll best be able to make a prediction for that place. In contrast, the LSTM actually is trained as a single model for all of these places combined. So we have one single model that we can just evaluate in 500 different places. And it turns out that this is the way of how, sorry, it's early here. The lights still go up. There it is. So it turns out that if you train this LSTM in this regional fashion by training a single model on all of the basins, it actually becomes much better than any of the conceptual models. So we actually have the comparison here where if we train the LSTM the way we train conceptual models, one model per basin, it actually isn't really better than some of the conceptual models. But only if we train it globally, meaning training it on all of the different basins combined, it really achieves this massive boost in performance. And the way that I like to think about this is that by sort of pooling the information from all of these basins, the LSTM really learns to transfer knowledge across space. So consider the example where we're asking the model to make a prediction for a certain basin for an event of a magnitude that it just hasn't seen for that basin in the past in its training data. Now, if I've trained a model only on the historical data from that basin, it just hasn't ever seen anything like it. And so it'll be unlikely to make a good prediction. Especially deep learning models are not good if they have to go outside of their training envelope. And then in contrast, the regional model has a much higher likelihood that there has been a similar basin in this training set that actually has seen such an event of such a high magnitude. And then the LSTM is able to sort of transfer the knowledge of how that basin reacted to the precipitation and how it transformed that precipitation into streamflow, and transfer that knowledge to the basin that we're now asking it to make a prediction for. And this is really something that we're only seeing to happen when we train these LSTMs on large sets of basins. I think there's a question of how many basins this is happening. So this is, I think I said 500 basins. It's a bit more than 500 basins all across the continental United States. I will in a second show a map of what we do at Google, which is at a much larger scale. And yes, so the LSTM uses the location static characteristics as inputs, and that's exactly what enables it to relate these different basins to each other. So it can look at these static characteristics, like the soil type and the elevation and so on, and figure out whether it has a similar basin in its training set where it has seen some event of a similar type before, and then it can transfer the knowledge by means of these static attributes. So that's exactly what's happening. And it actually turns out that this type of regional or global training not only allows you to improve the performance in the places that you're training the model, it also allows you to make predictions in places, to make accurate predictions in places where you don't have any training data at all. So this problem is known in hydrology as the prediction in ungauged basins problem. And it's one of the sort of biggest problems in hydrology that have been unsolved for an extremely long time. And now with an LSTM, because it gets these static attributes, we can actually apply that LSTM to sort of any place we like and just feed it the meteorological information and the static attributes of that place, no matter if it's seen that during training or not. And we can still generate predictions. And so what you see on this plot here now is the solid orange line is still the same LSTM, still trained on the places that we evaluated. The red dashed line is SAXMA, which is a very popular classical hydrologic model. And it's also being evaluated still the same way. We train it in the places that we're evaluating it. And now the line with the stars is sort of the asymmetric evaluation where we're evaluating this LSTM in a way where it hasn't seen the places that we're evaluating it on. So the way we do this is by means of a k-fold cross-validation, where we train the basin on part of the training of the gauges, and then we evaluate it on the others, and then we do the same vice versa, and we end up with predictions that are ungauged for the whole training set. So what we see now is that, of course, we're getting a bit worse, or we're getting clearly worse than the LSTM that has been trained on the places. But we're actually still on par, if not better in many cases, to SAXMA, where SAXMA has seen these places and the pub LSTM has not seen the places. So this is really quite a massive improvement in the ungauged prediction performance. So you can use this regional training to improve your gauged performance, but it also improves this ungauged performance of places where you don't have historical records. And that's especially important for flood forecasting because, of course, there are a lot of regions in the world that do not have these physical measuring stations and that do not have the long historical records that we have, for example, in many places in the US and in Central Europe, but that's still where still people live and that are still getting flooded and where we still want to make flood forecasts. So to show sort of a more real operational example, this is actually the map of all of the training stations that we use to train a single model for our operational flood forecasting system. So the colors don't really matter too much here, but what you see here is about 17,000 locations sort of all around the world that we're feeding the model during training in order to make it learn this very generic or generalizable behavior that then transfers to other places in the world. Nevertheless, of course, you still see that there are regions that are much more densely populated with gauges than other regions. And that's definitely still one of the big bottlenecks that we have for hydrologic modeling, is just if we had much more training data in the places that are underrepresented here, we would certainly be able to much better make predictions in these places. Because of course, it's much easier to generalize to an ungauged place that is right next to a gauged place, like these densely covered regions in the US, than it is to make predictions in this very sparsely covered area, let's say in many places in Africa. I think there was just a question of the temporal resolution. In this particular model, we're doing daily predictions, so one prediction for every day. We also have some research around doing hourly predictions or like generally higher resolution predictions. But for this operational global model, we're doing it at an hourly resolution. Sorry, at a daily resolution. Okay, so adding more training gauges is really one very effective way of improving your model quality. But it turns out that there is an sort of an orthogonal way of further improving the model. And this additional way is to not add more gauges, but rather to feed the model with more input data products. So if you remember in this earlier slide, I showed that we're feeding the model these weather information of precipitation and temperature and so on. And I just had this one time series that we're just inputting into the model. But actually, in reality, you have several data providers that will all give you their estimate of what they think today's precipitation is going to be like, or what they think the weather will be like in the next couple of days. And with a classical hydrologic model, you can really only feed one type of precipitation into the model at a time, and you don't really have much more that you can do. But with these flexible data-driven models, you can actually just feed all of that information into the model and just have it learn how the different data products are sort of wrong, each one in their own way. And you can learn the synergies between these data products, meaning that the different models, the different inputs might have a different error structure, and so the LSTM can now learn that error structure and draw much more information from the synergy of all of those inputs. And so what you see in this chart here is, again, the solid orange line is the same line that you've been seeing from the LSTM all the time. And now the line with the dots on it is the same model, except that now it's getting 3 different weather forcing inputs instead of only one of them. So this gap is almost as big or about as big as the gap between the conceptual model and the LSTM. So you're kind of doubling your advantage over the conceptual models just by feeding it more information about the weather. And of course, as we increase our ability to predict the weather more accurately, we're also going to be increasing our ability to then predict the stream flow. So adding more forcing data is really a very effective way. And in practice, we don't only use 1 or 2, we actually use 4 to 5 different weather forcings to train our models. So what you see here is kind of the temporal coverage of all of the different input data products that we use. GraphCast and ECMWF-HRES or IFS are the 2 forecast data products that we use. So GraphCast is Google's own internally developed weather forecasting product, which is also open source. And then HRES or IFS is from the European Center of Mid-Range Weather Forecasting, which is sort of one of the state-of-the-art global numerical weather forecasting models. So those 2 give us really their estimate for what they think the weather will be like in the next couple of days. We're using up to a 7-day lead time of those 2 models. And then we have 2 additional precipitation nowcast products, IMERG and CPC. So those really give us the historical context all the way up until today of what they think sort of the amount of precipitation was on each one of those days. They don't tell us what they think the future will be like, but it's still extremely useful, of course, to know what the past leading up until today looked like in terms of precipitation. And then for training, we also use ERA5 Land. We don't use that in real time because ERA5 Land is a reanalysis product, and so it's only produced sort of after the fact. And then we have the streamflow records, of course, which are our labels during training. So you can see here how each of these data products has a different sort of temporal coverage, but we're feeding all of them into the model to make the most accurate prediction that we can, given the information that we know. Now, the question is, of course, how do we get all of this information into the model? And that sort of leads us to the architecture of the model, how does the model deal with the fact that, for example, we have these different types of inputs that some of them are forecasts, so they have a lead time dimension of up to 7 days into the future, and some of them, like IMERG and CPC, are only nowcast products, so they sort of stop at the current day. So if we look at an architecture, we need an architecture that is somehow able to ingest data that has a different dimensionality between the hindcast and the forecast section. So now we're getting a bit more into the deep learning section of the talk, where we have this LSTM that we roll out over time, as I said, and we start, as I said, with this 1 year of historical context. We feed the LSTM all of the information from all of those different data providers, all the way until sort of the current day, the issue time, which is this time step number 365. And then we need to figure out somehow how to run the LSTM forward in time when we only have IFS and GraphCast, so only the two forecast products available. And the way that we used to do this in early hydrologic models was that we actually used two LSTMs that handed off the processing to each other. So the first one would process the hindcast period. It would then hand off the processing to a second LSTM that takes the state from the first one and then only takes the forecast information. We can't just naively run the hindcast LSTM all the way into the forecast lead times, because just the input dimensions wouldn't match. We would suddenly only feed it two input data products, and there would just sort of be two empty slots, and the model wouldn't know what to do with it. I think there was just a question of what is hindcast versus forecast. What I mean by that is information about the past versus information about the future. So the hindcast is really the context that we have. If I want to make a prediction today, what has the weather been like over the last year? And then the forecast is the prediction of these weather models of what they think the weather will be like in the next 7 days. I hope that sort of clarifies hindcast versus forecast. And so we had this model. We were reasonably happy with it until we actually did a plot where we plotted our lead time predictions at every issue time. So what you see here is this time series plot where the x-axis is time and the y-axis is our streamflow prediction. And at every point in time, we're plotting the prediction we made for the next 7 days. So at every point in time, you see a line starting that goes for the next 7 days. And you see this terrible behavior where, especially in this rising limb around April 2018, the model would every day say, well, tomorrow the streamflow is going to be a lot lower, and then it'll start rising again. And then the next day, it said, well, never mind, it was actually a bit higher, but tomorrow it's going to be lower, and then it'll start rising. And so it has this inconsistency where it always says that tomorrow is going to be different than what it actually says tomorrow. So ideally, I would like, of course, my forecast for tomorrow that I make today should be the same as my nowcast that I make tomorrow. So it should be consistent over time. So the lines should sort of align here, but they don't. And eventually we figured out that the reason for this happening is really this break in continuity in the processing that we have between the hindcast and the forecast section of these two LSTMs. Because we're sort of switching to an entirely different model here, we have this break in the distribution and in the continuity. And so that's why we see the model being inconsistent between the first and the subsequent time steps here. So that's obviously not a good model, and we would like our model to not have this property. And so we had to figure out a way of building a model that is able to be rolled out over the entire time series without this break between hindcast and forecast. There's always going to be some break because we just have reduced amount of information in the forecast section, but at least we would like to be able to run one LSTM into the future. And the way that we ended up doing this is what we call the mass mean embedding. So what we do there is or the purpose of this embedding network is to provide a consistent input to the LSTM, no matter how many of the input data products are available. So for the hindcast time steps, I will have all 4 of these input time steps available. And then in the forecast, I will only have 2 of them available, but I still want to get this consistent embedding that I can feed into my LSTM. And the way that we do this is we have a fully connected network that takes each of these data products individually and transforms it into an embedding. So in this example, we have these 3 forcing groups here. You can imagine them as 3 of those data providers, like ECMWF, GraphCast, and CPC. And in this example, the middle one is just missing at this time step, maybe because it's not a forecast product and we're in one of the forecast time steps. So we end up, after this fully connected network, we end up with two embedding vectors. And an embedding vector is really just a vector of a certain size, a fixed size that we have sort of predetermined. And we end up with as many embedding vectors as we have available for forcing data products at this time step. And then all we do is just we average those embedding vectors, which gives us this masked mean representation that combines the information that was available in all of these input data products, in all of them that were available at the time step, of course. And so then we have this embedding vector of a fixed size, and the size is fixed no matter how many data products I have available at the current time step. And so I can feed that into the LSTM, and now I'm able to run that LSTM all the way from the hindcast into the forecast portion of my input period, because the masked mean embedding is sort of dealing with the fact that some of the data is missing some of the time. So now I've gotten rid of this discontinuity in the processing in the LSTM, and I don't have the figure here, but this lead time plot that I had, like this plot here, is now looking much more smooth with this type of architecture. And this is actually also the architecture that we're now using in production to issue our flood forecasts. The figure here is slightly simplified, but it really gives you the idea of how we do the processing. And this masked mean embedding actually has the additional advantage that it makes us robust against missing data products. So you can imagine if you run a real-time system with 4 different data providers, once in a while, one of them will just have an outage and not give you the data in time. And of course, if that happens, you still want to be able to make a prediction yourself, because you can't just say, well, I couldn't warn you of that flood because GloFAS had an outage yesterday. And so this masked mean embedding can sort of seamlessly deal with that by just ignoring missing data products and still allowing us to run the LSTM and generate the forecasts. So that's nice. Not a number of fields are really the fields where we are missing the input for sort of any reason, either because, like in the example illustrated here, CPC is not a number in all of the lead time forecast time steps, because CPC does not give us information about the future. It does not give us information about the lead times. And so we just don't have a number that we could put into the LSTM for CPC for the forecast time steps. We could also have not a number scenarios where during these outage scenarios that I described earlier. So that's what I mean by not a number here. All right, so this is Google's hydrologic model today. And then, of course, we did a lot of evaluations of how well that model works. And I'd just like to show one of them, which is sort of the most recent big and thorough evaluation that we've done. It's been done on a slightly older version of the Google model, but it's only improved since. And what you see here is a comparison, a bit of a different comparison than what I showed earlier in the benchmarks, where we're comparing against the EU's Global Flood Awareness System, GloFAS, and we're comparing the ability of these models to predict 5-year return periods events. So events that we expect to happen only once in every 5 years. And we're evaluating this in F1 score, meaning some measure that combines recall and precision, and larger values are better. And what you see in this blue box all the way on the left is GloFAS's performance of GloFAS's nowcast. So GloFAS's ability in predicting 5-year return period events on the day that they happen. And it has a certain F1 score. And then in the subsequent boxes, the orange boxes, we're seeing the LSTM's model, the F1 score of the LSTM model at the different lead times. And so what we see is that about at a 5-day lead time, the LSTM is about as good as GloFAS's nowcast. In other words, that means where GloFAS can warn you on average about something on the day that it happens, the LSTM model could have warned you 5 days earlier, because you're gaining 5 days of lead time in making these predictions. And then, of course, the F1 score increases as the event comes closer to the nowcast time step. So the F1 score is higher in these earlier lead times. We actually have the newest model that we have. We're estimating it to be at the quality of GloFAS at around the 7-day lead time. I don't have a figure for that yet. We're hoping to publish this soon as well. So this is the benchmark. And then finally, I'd like to just give a bit of an overview of things that, GloFAS also has different lead times. Unfortunately, we were only able to evaluate the 0-day lead time there. You can find all the details in the paper that I've written down there. It appeared in Nature, Global Prediction of Extreme Floods in Ungauged Watersheds. So to close, I just like to give you a bit of a glimpse into the future of what we're currently researching and working on, and what will hopefully eventually become sort of the next generation of flood forecasting. Because of course, with all the results, the great results that I showed earlier, there are still a lot of conditions and things where the model is just not performing as well as we would like. So there is still definitely room for improvement. And one of the things where the current models struggle is what I called here spatial awareness. So if you consider this example where I would like to make a prediction at this red gauging location for, this is actually the Danube in Central Europe, and you have this huge upstream area which covers multiple countries, and it's a really large area. And in the way that I described modeling so far, you would just average your precipitation inputs and just feed the model a single time series of precipitation for this whole area. And what that means is the model has no idea whether rain is happening all the way upstream in the basin or all the way downstream. But of course that matters, because if it's happening all the way upstream, the rain will, or the water will actually take some time until it reaches the gauge, and so the streamflow response will be delayed. Whereas if it's raining all the way downstream, the streamflow response will be much more immediate, and so the model needs to know whether rain has happened in order to make an accurate prediction of the streamflow at the gauge. But this modeling approach that I showed so far just has no idea about it, and so it can't really make a perfectly accurate prediction here because it's lacking information. It's lacking this spatial awareness. Now, it turns out that this is not a new problem with deep learning methods. This has been a problem for classical models as well. And hydrologists have figured out the solution that they call distributed or semi-distributed modeling. And so what they do there is they take this large basin and they subdivide it into lots and lots of small subbasins that each drain into each other and sort of route the water towards the gauge. So you can imagine this at a more conceptual level as a graph, where each of the nodes that you see here in the graph represents one of these subbasins, and then the edges that connect these subbasins are the downstream drainage relationships where the upstream subbasin drains into a downstream subbasin, and they sort of converge all the way until they reach the outlet. And now with this structure, we can actually build models that model the streamflow at the subbasin scale and that get the meteorological information at the subbasin scale. And so we can build models that are much more spatially aware of where inside of the large basin the events are happening and how the water is routed towards the gauge location. And so we can get a much more spatially accurate information and much more spatially accurate predictions out of this. So is the hope. We're currently working on this. The idea is to use graph neural networks for this, because we have this graph structure here. And so we can combine this LSTM structure with the graph in order to make the model sort of learn this routing behavior of the water flowing downstream. I won't go more into detail in this. I'm happy to talk more about this. But for now, I'll sort of leave it here. And I'll close with a bunch of resources that might be interesting to folks. I already saw some questions in the chat around an API. So we have a number of different resources that might be interested to folks who are sort of working or want to work on this problem. The first one is Neural Hydrology. This is our sort of research grade code base where we have open sourced a lot of or probably all of the benchmarks that you saw in this paper, in this presentation. They're generated with Neural Hydrology, and it's a library, it's a Python library that really allows you to relatively easy set up your own streamflow LSTM and train your own models or evaluate your own models on whatever data you have available. The second research is Caravan. Caravan is really sort of a community project to gather as much streamflow data as we can. So I showed earlier in this talk this slide where you saw that models just get much better if you train them on many on the streamflow information from many basins combined. And so Caravan is this initiative to try and pool all of the streamflow information that individual researchers and agencies and so on have available, so that everyone can train their global models on this large data set. Caravan also has an extension called Caravan Multimet, which provides you with the meteorological information for all of the basins that we have streamflow for, so that you can run these multi-forcing models yourself that I showed earlier in these slides. And then finally, the last link leads you to Google's flood forecasting website, which has a link to the Flood Hub but it also has links to our API. So we have an API where you can sort of programmatically query our forecasts in pretty much real time. If you are interested in this, you will find instructions of how to get access to this API on this website. We also have a data set of historical reanalysis and reforecasts from the model that we use in production. So if you're interested in not getting the real-time data or the real-time forecast, but you're interested in getting historical records of sort of what would we have predicted at the time that this certain event was happening, you can download these, or you can access these data sets also under this link. I hope I've covered all of the resources that there are. If there are any more things that you're interested in, feel free to definitely reach out to me or anyone from our team, and we'll be happy to sort of direct you there. And with that, I think I'll stop here, and I'll be happy to answer some more questions. Probably I also missed some of the things that happened in the chat.
Thanks so much, Martin. That was really, really fascinating. I don't know much about flood forecasting, so that was very eye-opening for me. There are a couple questions in the chat that you may have, probably that last one from GOA. Will LSTM be heavily learning river discharge trending rather than hydrological processing?
So okay, I see what the question is about, and maybe there the thing that I should explain here to make this clear is that the model is actually not using river discharge or stream flow as an input. It's purely learning the stream flow response from the meteorological data, and so I think the question was aiming at whether the model just learns to sort of extrapolate the historical discharge into the future, but that's not happening because the LSTM is not getting that historical discharge as an input. It's only getting it as labels during training to sort of tune the model to, or have the model learn how precipitation and weather translates into stream flow, but we're not feeding it historic or real-time stream flow information. The only caveat to that, or the only exception to that, is certain regions, especially around India and Bangladesh, where we have partnerships with local governments, and there we do get real-time stream flow information, and there we do feed the model that information. But that's a different model that we're using there from the model that we're using sort of more globally. Hope that answers the question.
Good stuff. There's another question about collaborations. How can academics collaborate on this initiative?
Yeah, so we do pretty extensively collaborate with both academic institutions, but also with sort of environmental agencies and NGOs and other organizations. If you have a project that you think would be good, would be a good collaboration, definitely feel free to reach out to us, and we can see if that's something we can make happen. We're also sort of very active in the academic space. Everything we do is very open. We go to the conferences. So we're always happy to collaborate.
Stuff. I think, is there any more questions from people in the crowd?
Digital elevation data is sort of indirectly used as an input, yes. One of the ways that it's used as an input is just as part of these static attributes that I showed in the beginning, where we're just telling the model what is the average elevation of that basin. And then implicitly it's used for the actual delineation of the basin. So in order to know what the relevant area is for which we need the meteorological information, the elevation profile is sort of the key information to delineate the basin. But we're not feeding it an explicit map of the elevation in space. That is something that might go into the inundation model, but not into the hydrologic model.
And another one's just come up about how this service could fit in with the Bureau. I think Scott somewhat answered that in the chat earlier. How do you think Google's flood forecast could fit in with the Bureau of Meteorology's services?
So yeah, I'm not sure if we're immediately in contact with the Australian National Weather Service, but we are definitely in contact with some of the national weather services and some of the agencies that produce these forecasts. I think there's a number of different ways I can answer these questions. One of them is the model that we are building is really a global model, and so it's, at least at the moment, is using global weather data as inputs. And that global weather data is certainly less accurate than much of the local weather data that you might have available specifically for Australia. And that is definitely something that is limiting the model quality. So there is this trade-off between building these extremely global models, as we do, because we want to sort of be able to make predictions everywhere on Earth, and especially in regions that are sort of underserved so far, versus building these more localized models for individual countries, which is typically what these agencies are doing. But there is definitely a lot of interest in many, if not all of these agencies to sort of start exploring these deep learning types of architectures, because they could certainly be applied also at the national scale. Many of the benchmarks that I showed were just at the national scale of the US. And there is also, you saw probably on the map that I showed earlier, there's a lot of gauges in Australia. So building LSTM-based models is definitely something that can also be done at the national scale. And I think it's happening more and more that these weather agencies and these flood forecasting agencies are getting aware of this and starting to build their, or to at least explore their own models. Certainly, this is a slow process. There's existing systems that need to be replaced, or that would have to be replaced, and that need to be, and the new system needs to be proven. But I think it's sort of slowly happening.
Super. All right. Oh, sorry. There was one more then. How can elasticity and rainfall runoff relationship can be translated to the LSTM model? Have you encountered this problem that the relationship in some catchments might have shifted?
Right. So if I understand correctly, this question is aiming at things like maybe even climate change, where over time the streamflow response or just the general behavior of the basin will change because of climate change or because of other factors. To some degree, we can just solve that by, if we regularly get updated streamflow records, historical records, we can just retrain our model and it'll learn sort of the new behavior, and therefore it will sort of gradually adapt as the system is changing. Now, unfortunately, of course, in many of the places that we're modeling, especially in the sort of underserved regions, we might have some years of data from 1980 and then nothing ever since. And so in these cases, it's of course a much harder task to even just evaluate whether the model is still doing a good task. And we're seeing that the model is to some degree definitely able to adapt to these changing behaviors, even if it's not getting updated streamflow labels. And this is again happening because, let's say if the weather data is changing, the model can use this regional training approach to find basins that are similar to the new behavior of the basin, and transfer the knowledge of how this new basin is behaving, or how this changed basin is now behaving. So we've actually done these experiments where, or we have this illustration where you can imagine that maybe some basin in Germany, as the climate becomes hotter, it becomes more similar to basins in Spain. And so because the model has also seen these basins in Spain, it can now transfer that knowledge of how the basins in Spain behave to how the basins in Germany behave sort of after these changes. It's definitely something that is more challenging, and that does not always work. But generally speaking, there is at least some capability of the model of doing that. What's much harder, certainly, is human influences. So if someone just builds a dam somewhere on the river and we don't have information about that, certainly it will be much harder to model that, because now suddenly the streamflow prediction is affected by sort of the human operation schedule of that dam. And that is something that we currently have a very hard time, if it's possible even at all, to sort of model this. Also because there's very limited data only available on these human influences and these sort of operating schedule of dams and reservoirs, for example.
All right. Amazing. Once again, thanks a lot, Martin.
Yeah.
There was a question in there if you can share your email.
Yeah, it's right there.
Oh yeah, there we go. Gauch@google.com. So yeah, thanks everyone for joining us. We've got a few more events in the pipeline. Be sure to check it out at the G2G AI for Science webpage. Please, you can share some feedback. I just posted a link in the chat. Otherwise, thank you once again, Martin, and we'll see you all again sometime soon. Good stuff.
Thanks, everyone.